Welcome to this coding walkthrough. Today, we'll be solving LeetCode problem number 832, flipping an image. In this problem, we work with a binary matrix and perform two operations, flipping rows horizontally and inverting binary values. Stick around as we break this down step by step. In this problem, we are working with an nxn binary matrix called image, where every element is either a 0 or a 1. Our goal is to transform this matrix by performing two operations. First, we flip the matrix horizontally, which means reversing the order of elements in each row. Then, we invert it, which means replacing every 0 with 1 and every 1 with 0. After completing these two steps for all rows in the matrix, we return the modified binary matrix. The input is formatted as a 2D array where each row contains binary integers, and the matrix is square, meaning it has the same number of rows and columns. The output is also a 2D binary matrix that reflects these transformations. Let's look at an example to understand this better. Suppose the input matrix is 1 1 0 1 0 1 0 0 0. The first step is to flip each row horizontally, which involves reversing the elements in each row. After this step, the matrix becomes 0 1 1 1 0 1 0 0 0. Next, we perform the inversion, where each 0 is replaced with 1 and each 1 is replaced with 0. Applying this transformation, the final matrix becomes 1 0 0 0 1 0 1 1 1. This is our output for the first example. Now consider another example where the input matrix is 1 1 1 0 0 0 1 0 1. Again, we start by flipping each row horizontally. In this case, reversing the rows doesn't change their order since they are symmetrical. The matrix remains 1 1 1 0 0 0 1 0 1. Then, we invert the elements. After replacing 0 with 1 and 1 with 0, the final output is 0 0 0 1 1 1 0 1 0. This demonstrates how the process works for different types of input matrices. Finally, let's examine a smaller matrix, 1 0 0 1. Flipping horizontally means reversing the elements in each row, which transforms the matrix into 0 1 1 0. Next, we invert the values, changing 0 to 1 and 1 to 0. The final output becomes 1 0 0 1. To summarize, the constraints of the problem specify that the matrix size will be between 1x1 and 20x20. It's important to consider edge cases, such as when the matrix has only one row or column, or when all elements are the same. These scenarios can help ensure your solution is robust and handles all valid inputs correctly. To solve the problem of flipping an image, we break the task into two key steps for each row of the binary matrix. First, we perform a horizontal flip, which means reversing the order of elements in the row. Then, we invert the values, replacing each 0 with 1 and each 1 with 0. A straightforward way to implement this is the brute force approach. Here, we reverse the row using a built-in method, such as slicing in Python, and then manually iterate through the reversed row to invert each value. This approach is simple and easy to understand, as it directly applies the two operations sequentially. While the time complexity is O(n) squared, due to processing each row individually, it uses O(1) space since the operations are performed in place. However, reversing and then inverting separately can feel a bit redundant, which leads us to explore more efficient alternatives. A more efficient solution is the optimized approach, which combines flipping and inverting into a single pass through the row. Instead of processing all elements twice, we traverse only half the row, swapping and inverting the corresponding elements at the start and end simultaneously. For example, for elements at index I and n1i, we perform the flip by swapping their positions, and we invert them at the same time. If the row has an odd length, the middle element is handled separately by inverting it directly. This method is more efficient than the brute force approach because it minimizes redundant operations while maintaining an in-place implementation. It has the same time complexity of O(n) squared, but avoids unnecessary passes over the data, making it a cleaner and faster solution for larger inputs. Another approach to consider is creating a new matrix for the result instead of modifying the input matrix. In this method, we calculate the flipped and inverted version of each row independently and store the results in a separate matrix. While this avoids in-place operations, making it easier to debug or trace, it comes at the cost of additional memory usage. The space complexity is O(n squared), as the new matrix requires storage proportional to the size of the input. This makes it less efficient for larger matrices, even though the time complexity remains O(n squared), just like the other approaches. Overall, while this method can be useful for certain cases, it is less suited for scenarios where memory efficiency is critical. For these reasons, the optimized approach strikes the right balance between efficiency and resource usage, making it the preferred choice. The key insight that simplifies this problem is realizing that flipping and inverting can be combined into a single operation. Specifically, flipping the binary value can be achieved using the formula 1 minus the value, and swapping elements at indices I and n1i simultaneously handles the flipping step. For odd-length rows, the special case of the middle element is efficiently managed by directly applying the inversion. Comparing the approaches, the brute force method is easier to implement but results in redundant passes over the data, making it less efficient. The optimized approach eliminates this redundancy and avoids additional memory usage, making it preferable for larger inputs. While the alternative method simplifies the logic by using a new matrix, its O(n squared) space complexity becomes a significant drawback when working with large matrices. By choosing the optimized approach, we achieve a solution that is both resource efficient and straightforward to implement, making it ideal for this problem. To solve the problem of flipping and inverting a binary image, we start by understanding the input and breaking down the problem into manageable steps. The input is a binary matrix where each element is either 0 or 1, and we need to process each row independently. The first step is to iterate through each row of the matrix using a loop. For a matrix with m rows and n columns, this means iterating m times. Next, we flip the row horizontally by reversing the order of its elements. This can be done easily in Python using slicing, such as row::(1), or by swapping elements iteratively. For example, if a row is 1, 0, 1, reversing it results in 1, 0, 1, because it's symmetric. However, for a row like 1, 0, 1, 0, reversing it produces 0, 1, 0, 1. This flipping simulates a horizontal reflection of the row as if it were mirrored along its center. After flipping a row, we move on to inverting it. This involves replacing each 0 with 1 and each 1 with 0. In Python, this can be done in place by iterating over the row or by using a transformation function like one element for each value. For example, if the flipped row is 1, 0, 1, inverting it gives 0, 1, 0. The reason this works is that subtracting a binary value from 1 effectively toggles the bit. Once the row is inverted, the result needs to be stored, either by modifying the original matrix directly or by creating a new matrix to store the processed rows. After all rows are processed, the final matrix will reflect both the horizontal flipping and the bitwise inversion. Additionally, these operations can be combined in one pass. Instead of reversing the entire row first and then inverting, you can swap and invert elements simultaneously. For instance, in a row like 1, 0, 0, 1, you can swap and invert the first and last elements in one step, reducing the number of operations required. Performing these operations in place further optimizes the process. Both flipping and inverting can be completed without requiring additional storage, which reduces the space complexity from O(m*(n) to O(1). There are a few edge cases to consider as well. For rows with odd lengths, the middle element, if present, should be inverted. An empty matrix can be returned unchanged, and rows consisting entirely of zeros or ones do not require any special handling as the operations are straightforward. From a data structure perspective, the matrix is naturally represented as a 2D list in Python, making it easy to process. Temporary variables can also be used for swapping elements during the flipping step, but they are optional. When analyzing the time complexity, iterating through m rows of the matrix, each with n columns, results in a time complexity of O(m*(n). Breaking this down further, flipping and inverting each row individually takes O(n) time. Since we process all rows, the combined time complexity remains O(m*(n). The space complexity, on the other hand, is O(1), because the operations are performed in place, meaning no additional memory is required aside from the input matrix itself. To summarize the approach, the pseudocode for this algorithm is as follows. Define a function flip_n_invert_image that takes the matrix as input. For each row, use two pointers, left and right, initialized to the start and end of the row respectively. While left is less than or equal to right, simultaneously flip and invert the elements at these positions using the expression 1 row, right, and 1 row, left. Increment the left pointer and decrement the right pointer to move inward. After processing all rows, return the modified matrix as the result. Let's walk through an example to see how the algorithm works. Suppose the input matrix is 1, 1, 0, 1, 0, 1, 0, 0, 0. For the first row, 1, 1, 0, flipping it produces 0, 1, 1, and inverting it gives 1, 0, 0. For the second row, 1, 0, 1, flipping results in 1, 0, 1, and inverting transforms it into 0, 1, 0. Finally, for the third row, 0, 0, 0, flipping has no effect as the row remains 0, 0, 0, but inverting it yields 1, 1, 1. The final output matrix after processing all rows is 1, 0, 0, 0, 1, 0, 1, 1, 1. This demonstrates how the algorithm efficiently combines flipping and inverting to transform the binary image as required. The code solves LeetCode problem number 832, flipping an image. The problem requires flipping each row of a binary matrix horizontally, followed by inverting the values, changing 0 to 1 and vice versa. This is achieved efficiently in a single pass per row. Explanation. 1. Outer loop. The function iterates through each row of the image using a for loop. 2. Flipping and inverting. Inside the loop, we use a nested for loop to process the first half of the row, including the middle element if the length is odd. For each pair of elements, one from the beginning and one from the end of the row. The swapping is performed using row I1 equals, which efficiently exchanges the elements at I and I1. The inversion is done by applying 1x to the elements, flipping 0 to 1 and 1 to 0. 3. Edge case handling. The code handles rows of any length, including odd lengths, where the middle element is inverted in place. For time complexity, the algorithm processes each row in O, n, time, flipping and inverting in one pass, resulting in an overall complexity of O, m asterisk n, where m is the number of rows and n is the number of columns. 5. Space complexity. The solution is in place and uses O1 extra space. This ensures the solution is both efficient and concise, adhering to the problem's constraints. This is the Java implementation of LeetCode problem number 832, flipping an image. The code mirrors the Python logic, where each row of the image is reversed and its elements are inverted. Key differences include explicit type declarations for arrays and variables in Java, and the use of bitwise XOR, for inversion instead of arithmetic, 1x, from the Python version. The implementation iterates through each row, swapping and inverting elements at symmetric positions within a single loop. The solution ensures efficient handling of the problem within O, n asterisk m, time complexity, where n and m are the row and column dimensions of the image. In this problem, we are working with a binary matrix, which means the matrix only contains zeros and ones. The task involves two transformations. First, we flip each row horizontally by reversing the order of its elements. Then, we invert the image by replacing every 0 with a 1 and every 1 with a 0. To make this clearer, let's take an example matrix 1, 1, 0, 1, 0, 1, 0, 0, 0. The solution will process each row step by step. Starting with the first row 1, 1, 0, we reverse it to get 0, 1, 1. After flipping, we invert each number using the formula 1x. This means the 0 becomes a 1, and the 1s become zeros, resulting in 1, 0, 0. We'll now apply the same steps to the other rows to complete the transformation. For the second row, 1, 0, 1, reversing it gives 1, 0, 1, which happens to remain the same. Then, we apply the inversion step. The first and last elements, both 1, are flipped to 0, while the middle 0 becomes 1. The result is 0, 1, 0. Now for the third row, 0, 0, 0, reversing it doesn't change the order since all elements are identical, so it remains 0, 0, 0. When we invert this row, each 0 is replaced with a 1, resulting in 1, 1, 1. Combining the processed rows, the final matrix is 1, 0, 0, 0, 1, 0, 1, 1, 1. This demonstrates how the flipping and inverting transforms the input matrix into the desired output. Let's consider another example with a smaller matrix, 1, 0, 0, 1. The first row, 1, 0, is flipped to 0, 1. Then, inverting the elements gives 1, 0, as the 0 becomes a 1 and the 1 becomes a 0. For the second row, 0, 1, flipping it results in 1, 0. After inverting, the first 1 turns into 0, and the last 0 becomes 1, producing 0, 1. The final transformed matrix is 1, 0, 0, 1. This example highlights that the flipping and inverting steps can handle matrices of any size, even smaller ones, with the same approach. Now let's examine a single element matrix, 1. Here, there's only one row and one element, so flipping it doesn't change anything, it remains 1. When we apply the inversion step, the single 1 is replaced with a 0, resulting in 0. The final output matrix is 0. This demonstrates that even the smallest possible input matrix can be processed using the same flipping and inverting logic, ensuring the solution is robust enough to handle all cases. An important observation about this solution is that flipping and inverting can be combined into a single loop for efficiency. Instead of reversing the row first and then inverting it in two separate steps, we can perform both operations in one pass by swapping and inverting elements simultaneously. This is achieved with the code row I1 equals 1 row I1, 1 row I. Additionally, we only need to process half of the row because flipping and inverting are symmetric. This optimization reduces unnecessary computations. The time complexity of this solution is O, n times m, where n is the number of rows and m is the number of columns, as each element is processed exactly once. The space complexity is O1, since all operations are done in place, without requiring extra memory. This makes the solution both time and space efficient, perfectly suited to meet the problem's requirements. To analyze the time complexity of this algorithm, let's break it down step by step. The input is a binary matrix of size nxn. For each row in the matrix, the outer loop runs n times, as there are n rows. Now, within each row, the inner loop processes only the first half of the elements. For odd-length rows, this includes the middle element. So, the inner loop runs approximately n/2 times for each row. Inside this loop, two key operations occur, swapping two elements and inverting their values. Both of these operations are constant time operations, or O1. This means the total work done for one row is proportional to n/2, which simplifies to O(n). Since there are n rows, the total work for the whole matrix is n rows multiplied by O(n) work per row, leading to an overall time complexity of O(n squared). Therefore, the algorithm processes the entire matrix in quadratic time. Now let's consider the space complexity of this algorithm. The key insight is that the algorithm operates directly on the input matrix, modifying it in place. This eliminates the need for any additional data structures to store intermediate results. The only extra space used is for loop variables and a temporary variable for the swap operation, all of which require constant space, or O1. While the input matrix itself requires O(n squared) space, this is not considered additional space since it is part of the input. If we compare this to a brute force approach, which might involve creating a separate matrix to store the transformed values, that would require an additional O(n squared) space for the new matrix. By avoiding this extra storage, the optimized approach reduces the auxiliary space complexity to O1. Therefore, the space complexity of this algorithm is constant, O1. In summary, the algorithm has a time complexity of O(n squared), reflecting the need to process every element in the matrix, and a space complexity of O1, as it operates in place without using additional memory. This optimized approach is more space efficient than a brute force alternative, which would require extra O(n squared) space for a new matrix, while maintaining the same time complexity. By directly modifying the input matrix, the algorithm strikes an effective balance between simplicity and efficiency. When working on flipping and inverting an image, there are some common mistakes you'll want to avoid. First, the order of operations is crucial. Flipping the row horizontally must always come before inverting the values. Doing these steps in the wrong order will lead to incorrect results. Another issue arises when flipping a row in place. Without careful index handling, such as properly swapping row I with row ni1, you may encounter index errors or accidentally overwrite values. Additionally, binary inversion can trip up developers who use the bitwise not operator, thinking it will work for binary matrices in Python. Instead, the correct approach is to use 1 cell 4 inversion, which directly toggles between 1 and 0. Edge cases must also be handled properly. Examples like single-element rows or empty matrices can easily cause runtime errors if overlooked. Finally, while it may be tempting to use extra space for flipping and inverting, this approach is inefficient and might violate space constraints during an interview. Always aim to modify the matrix in place whenever possible. To perform well in interviews with this problem, it's important to recognize the key patterns involved. This problem combines two fundamental operations, reversing arrays and manipulating binary values. Mastering how to reverse arrays in place is a skill that will frequently come in handy. The optimal approach here is to perform both flipping and inversion in a single pass for each row, which ensures the overall time complexity remains efficient at O and *m, where n is the number of rows and m is the row length. As you solve this, be ready to clearly explain your reasoning for flipping before inverting the values. Interviewers often assess your clarity of thought and whether you handle these operations logically. To validate your approach, it's helpful to walk through a small example matrix step by step, ensuring your solution works as expected and addressing any edge cases. You may also want to explore related problems to deepen your understanding, such as LeetCode 344, which focuses on reversing arrays, or LeetCode 48, which involves more complex matrix transformations. There are also alternative approaches to solving this problem, each with its own benefits and trade-offs. A simple two-pass approach involves first reversing the row and then performing the inversion. While straightforward to implement, this method is less optimal compared to a one-pass solution. For those comfortable with Python, a functional approach using list comprehensions or the map function can be used to perform both steps in a compact, elegant way. However, this style may be harder to grasp for beginners. A more advanced variation involves first transposing the matrix and then applying similar flipping and inversion operations. While this approach isn't required to solve the problem, it's a great way to explore more complex matrix manipulations. As you consider trade-offs, think about whether to prioritize in-place operations or use extra space. In-place solutions are memory efficient but require careful index handling, whereas using extra space simplifies the implementation but may not meet interview constraints. Similarly, aim for a balance between readability and efficiency. An overly optimized solution might be harder to explain, so in interviews, ensure your solution is both clear and effective. Great work! Today, we learned how to solve the problem flipping an image efficiently by breaking it down into two straightforward steps. Remember, mastering these types of problems builds a strong foundation for more advanced challenges. Thanks for watching, and don't forget to like, share, and subscribe for more coding tips. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!